Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome ladies and gentlemen. Please take your seat. We are ramping up for the second keynote of today, and I hope you have all enjoyed our evening outing yesterday where we have been to the City Hall of Stockholm. And as I mentioned there already, we are very fortunate to be in Stockholm around this time, which is the Nobel Week, where many of the Nobel Laureates are around. And I'm very pleased that one of the physics Nobel Laureates this year found time and will spend an hour with us here now. And so I'm very pleased to introduce to you Professor Brian P. Schmidt from the Australian National University in Western Creek. And he, together with his colleagues Adam Rees and Saul Perlmutter, won the Nobel Prize for Physics this year for the discovery of the accelerating expansion of the universe through observations of distant supernovae. He's going to tell us a little bit about that, but I guess he will make a little wider talk as well and talk about how astronomy meets data. So please join me in welcoming Professor Schmidt.
Thank you. Thank you very much. It's a great pleasure to be here. So I thought as part of the excitement this week, it would be fun to come and, talk to you guys a little bit. I'm very much a user of the work that's being done here. I wouldn't say I'm an expert. So I thought maybe I would put in context how the work we're doing in astronomy fits into the work that you're doing here and why it is so important. We actually have some of the experts in the field who I know personally from the past, George Stragosky and Dan Katz, who can give you real specifics on the astronomy if you want to get and ask them. So I've prepared this talk with a little bit of help from two people in Australia who work in this, Tara Murphy at the University of Sydney and Peter Quinn at the University of Western Australia. So when we go in astronomy, we look back, going way back. The work I look at, I was looking for exploding stars in the sky. And these have always been recorded as data. Of course, very primitively, initially, 1054, a supernova went off in the Crab, called the Crab Nebula, up in the northern part of the sky, and it was recorded in Chaco Canyon, in the United States, as an event, which we can use today to maybe not so much understand the event, but to know where it was and where it was seen. If we go back more locally here in Sweden, Tycho Brahe went through and recorded a supernova I have studied and whose observations are important. So going back to 1572, Tycho Brahe saw this new star in the constellation of Cassiopeia, which was what we call now a supernova, and is a type 1a supernova I'll talk a little bit about later on. It's a certain type of an explosion. It's a giant thermonuclear detonation, which the observations of Tycho Brahe allow us to now look back in time at the star that it exploded and to try to understand why these things explode. Because although I'm going to tell you about how I use them to trace back the history of the universe, the explosions of stars still remain a bit of a mystery. So astronomy has always been data intensive. If we go back to Galileo, when he invented the telescope, he recorded the positions of stars and took copious notes and made what was an Italian bestseller in 1612. Now, amongst those data, it's a shame that he wasn't able to put them on the internet and then go back and recall, because one of the things that he did in his little drawings in his book was to see Neptune 3 times. But he wasn't able to correlate it with anything else. He didn't have the technology. And so Neptune took another couple hundred years to be discovered. And so that is what the power of having modern data gives us, is the ability to do new and exciting things. If we look later on, when the telescopes became better, people were able to go through and sketch pictures, but those are not as useful as you might think for an astronomer. And eventually we got to the first photographs in the late 1880s, where people could actually make measurements which we can refer to today. So for example, one of the things that we like to do is to see how the stars are changing and how they're moving across the sky. So those first photographs provide a rough but useful record of what was going on. If you actually plot how technology is taking us, we can look at telescopes. Now, telescopes are what give us the ability to look back in time deeply. And so, from the time of how many eyes in the form of telescopes are on the sky, you can see that there's been a rapid increase from the time of, for example, Tycho Brahe, who really just had his eye, to the telescopes that came about in largely starting with Herschel in the late 1700s, and to what is going to culminate, hopefully in the next decade, on extremely large telescopes, such as what the US and Europeans are working on. And so these telescopes, of course, have increased things by an enormous fraction. But the doubling time is pretty slow. It's about every 20 years. If you go and look at the instrumentation, the ability to go through and record information, that's a different story. You went in the old days where Tycho Brahe would go through and write down numbers in a notebook, 1, 2, 3. Not a lot of bytes. If you look at now, we had photographic plates which recorded certain amounts of information, but now digital detectors are rapidly advancing and getting larger. And so the order of magnitude increase here is much, much larger. And it's doubling much, much quicker, much more quickly. Essentially doubling right now in our capacity of taking data about every year. So that is a little faster than Moore's Law, and it tells you we're going to bump into some problems here in the very near future. All right, so now let's go and talk about how this relates to what I do and the work that we've received the Nobel Prize for. So I realize not many of you here are astronomers, so I want to go through and really start at the beginning. Take you back to Vesto Melvin Slipher, someone almost none of you will know. Vesto Melvin Slipher went through and took the light from galaxies and spread it out into the colors of the rainbow to what we call a spectrum. And a spectrum of a star or a galaxy holds the fingerprint of atoms. These atoms absorb light at specific colors, and they allow us to identify the object. And when he looked at these objects, he found something he was surprised by. He saw that their light had been stretched to the red. And we can understand this as the Doppler shift, or at least that's how he understood it. If you have, for example, a BMW car coming towards you, you'll note that its lights are always blue. Now, that's actually not because it's coming quickly towards you, but if you could measure it very, very precisely, you would see that the light that it was emitted was shifted slightly to the blue. It was squished a little bit, the light was. If it's moving away from you, it's stretched a little to the red. What Slipher found was something quite funny in 1916. Almost every single object observed was moving away from us. And that was a cosmic conundrum in 1916, because since the time of Copernicus, we thought we lived in a very unspecial part of the universe, a place like everywhere else would see, and suddenly it would seem that everything was moving away from us. So we seemed a special, but not very popular part of the universe. And that took a little while to figure out. And it was figured out by doing a physics experiment. And that physics experiment was measuring distances. Now, astronomers are not good at measuring distances because we can't just lay a ruler down. We have to improvise. And the improvisation that we make is what we call a standard candle. That is, the further away a light bulb or a candle is, the fainter it appears. And so by measuring how bright an object, whose brightness you think you understand is, you can go through and judge distances. Edwin Hubble had access to the best technology that 1920s could provide, which was the Hooker telescope, a 100-inch telescope, way ahead of its time on the outskirts of Los Angeles near Pasadena. And this telescope allowed Edwin Hubble to go through and look at stars in nearby galaxies, the same galaxies that Slipher observed. Now, Edwin Hubble had to make an assumption, which was, if you've seen one really bright star, you've seen them all. And so he went through and just recorded how bright all the stars were in these galaxies of Slipher. And what he found out was the faster, sorry about the typo, the galaxy was moving, the fainter the stars. So that meant the faster the galaxy was moving, the further the galaxy was away. And Edwin Hubble then proclaimed when he saw this that that meant that the universe was expanding. Now, that may not be immediately obvious to you why that is true, so let me give you a little movie. Hubble's law. So here I have a map of the universe, and through the magic of my computer, I'm going to expand the universe a little bit. Now, let's look what happens when you overlap that expansion. You can see when you do this, I think, if you're here, that objects that are nearby have moved a little bit if I stretch the universe. Objects a long ways away have moved a lot. The further away you are, the faster you're moving away. Just what Hubble saw. Furthermore, I can change my perspective. I can move over the same expansion, and I see exactly the same thing. Everyone in the universe sees the same thing if the universe is expanding, and they see what Hubble saw. Now, I would normally talk to you about how Einstein and general relativity play into this, but I'm going to skip that because we need to move on. So, the experiment that one can imagine is that, imagine if we look at the universe and we look at distant objects. Now, because light takes time to travel across the universe, when you look a long ways away, you're looking into the universe's past. The further away you look, the further in the past you're looking. And so as the light travels through the universe, light is a wave whose color is related to its wavelength. That is, how close the troughs are here. And so as the light travels through the universe, it gets stretched by the expanding universe. And so when you go through and you see something, the reason its light is shifted to the red is because it has been stretched by the expanding universe. Now imagine if we wanted to go through and take a little measurement of the universe and see what it's going to do. If I have two galaxies right now, which are separated by a certain distance at a certain time, the rate that the universe is expanding is telling you how that's changing over time. And so if I have the rate that the universe is expanding, it just tells me the trajectory of galaxies in the universe. And you can see, if I measure the rate the universe is expanding, I can extrapolate back in time, and I can see where the Big Bang is. Now, the universe may be slowing down, because the universe is full of stuff like us, atoms, and also other stuff which has gravity. That gravity attracts the entirety of the universe, and so if the universe has a lot of stuff, it will slow down over time, and that slowing down of the universe will change the trajectory. The universe has enough stuff, the universe will reach a maximum size and eventually turn around and start to contract. So here we have the Big Bang, when you look back in time, and in this case, if the universe has enough stuff, you would get the Ganab-Gib. That's the Big Bang backwards. So how are we going to look back in the past? Well, we need a really bright standard candle. And the brightest standard candle that we have came to us via Tycho Brahe. And these are called Type 1a supernovae. Type 1a supernovae are very bright. They're 5 billion times brighter than our sun, and our sun is a number like 10 with 31 zeros behind it, brighter than a 100-watt light bulb. They're very, very bright. All right, so a supernova, as seen by Tycho Brahe, takes about 20 days to get bright, and then it fades away. So we know more or less how many watts these things are. And the way we started studying these really happened quite recently because they were very hard objects to find. We did not have the ability to control the data to discover these. And the work that was done was largely done in Chile by a group called the Colón-Tololo Survey. And these guys went through and used a clever, but maybe seems in the digital era, a slightly arcane way. But it was the only thing. So here's Jose Maza from the University of Chile with a photographic plate. And these would be they'd take a picture of the sky, and then they would go through and stick it in this machine, which allowed you to blink between the two plates. So your brain ended up being the computer. Your brain went through and said, I see something's changed. And the reason they did this is we simply did not have the computer power to to deal with this amount of data back in the late 1980s. This was a huge problem. We also didn't have the ability to digitally record the information. So this was the way progress was made. So the photographic plates were big enough to scan huge pieces of sky, and they were sensitive enough to find objects in the nearby universe. We could look back with these photographic plates about 1 billion years into the past. So photographic plates were great because you could make them almost arbitrarily large, but they were bad because it was very difficult to get useful digital information out of it. They also aren't very sensitive. A photographic plate is about 1% sensitive. 99% of the light goes right through the plate and disappears. And so that's why you could only look so far. Now, to do an experiment, we want to look and figure out what the universe's trajectory is and whether or not it's going to end eventually. That requires looking further afield. We need to go 5 billion years into the past. And so that was enabled in the early 1990s with new technology. Not so much bigger telescopes, but large CCD, charge-coupled device detectors, which are pieces of silicon with pixels that we can go out and used in many, many digital cameras. And so the idea would be, here's a single 2,000 by 4,000 pixel image, so that's 8 million pixels, or for us, 16 bits of information per pixel, so on order of 16 megabytes. And on this, there's about 4,000 galaxies. Now, supernovae are very rare. They only occur in a galaxy like the Milky Way, every 250 to 500 years. So we have to look at many, many galaxies. And these digital images were hard because we had to spot the supernova from this vast quantities of data. This is only 1/8 of one image that we would take every couple minutes. And so I can show you the supernova, which is here. And we don't identify a supernova just because it's a star next to a galaxy. We identify it because we took a series of images separated by a couple weeks apart, so we could see the new stars appear from nothing. Now, the digital processing that we had to do with this data was actually quite extreme. You have to take all these pixels, you have to map them, you have to then sort of go through and put what we call an image kernel, a convolution, a point spread function, which manipulates the way the stars look to match up. You subtract. Now, okay, you guys, you've got little mosaic programs and stuff that do that now. This did not exist in 1995. This was all homebrew by people like myself who had to do it. And so in 1997, I should also tell you that the data rates were quite high for people who did not have a serious group effort behind it. I was a postdoc. I was 27 years old when we started this effort. And so what we had access to were roughly 233 megahertz Pentium 2s. Some of you will remember those if you're old enough. We actually used 250 megahertz UltraSparks back then as well. They were just a little bit faster. But we were taking roughly 15 gigabytes of data with these machines, which are quite slow. And then the real killer was the fact that hard drives were typically 2 to 4 gigabytes in this era. And so we would take, 6 nights of data, and you would just need more hard drives than you could put on, all the computers in the place. And so we really just managing this effort of pushing the amount of data through all these disparate computer systems, which were in situ at the observatory and I had no control of. I spent all my time just trying to get operating system problems working. And so that effort wasn't quite intense. And we had to sift through that data quickly because we needed to find those objects and 24 hours later go to Hawaii with the data and say, look here, and take a specific spectrum of it to confirm how far away or how much the light of this object had stretched. And so that was an incredibly intense period where I can say that we did it by sort of guts and did it for the glory, but we certainly did not do it very efficiently. So one of the things that this organization, this gathering of people is to figure out how to do that in a real way using real hardware and real software rather than the sort of ad hoc way that we did it. So to give you an idea of what one of these trips was like, this is where we took the data in Chile. This is the CTIO 4-meter telescope. And we would go through, and as the sun set, Nick Sunsef, who co-founded the team with me, would come in and start telling the telescope to move through the sky. Now, you may think we're sipping our Chardonnay as we watch the sky goes by, but there's actually quite a bit of activity inside the dome, just making sure we're getting this regular stream of data. And then we get to the point of having to use the software, which sometimes worked, and then identifying all the possible exploding stars and separating the wheat from the chaff. And so this really was a multi-person effort. And as I said, we had to go very quickly because once you find one of these things and you decide, yeah, those are the real ones and those aren't the real ones, we had to ship the data by the internet, which was extremely slow back then. So to the top of Mauna Kea, to the Keck telescopes, where you would use the largest telescope in the world that had just been recently commissioned to go through, and here's Adam Rees and Alex Filipenko going through and taking spectra of the objects we had just discovered 12 hours earlier. So that was a good way for me to get no sleep trying to make sure that all happened. But in 1998, we were able to do the experiment of going through and looking into the universe's past. And so this diagram, which I don't really have enough time to explain, essentially shows nearby objects and distant objects. Here we're looking at objects, and if we go back, it shows that these objects in the past were fainter than we had expected, and if you see my full talk, I would explain why that means that the universe was accelerating. Essentially, these objects are further away than you would expect, and that means the universe had to be expanding faster and faster over time. Things are further away than we would have otherwise expected. All right, so you can see the importance of data. The reason we were able to do this is we lived in an era where we could cope with that data rate, and we could just barely cope. In the future, we're not going to be able to be so sloppy. So astronomy right now is in a golden age. We are still a frontier science. We are limited more by resources than inspiration, which is typical of a mature science. That is, you build us a better telescope, give us better instruments, we can do cool things. It's not about, we haven't run out of ideas yet. But we rely on large pieces of community-used infrastructure, telescopes. And telescopes have a single feature, is that they're really expensive. And so this telescope has got a lot of press recently in the United States for being particularly expensive, roughly $8 or $9 billion, the James Webb Space Telescope. But it's not the only one. Our future facilities, for example, the Giant Magellan Telescope, the 30-meter telescope, also known as the TMT, and here in Europe, the European extremely large telescope, are all billion-dollar pieces of infrastructure which we all want to use, but it behooves us to use them well. And since data is relatively cheap, that's a place where we can really get the most out of these telescopes. We need to get the most out of the new telescopes we're building, and so we're building increasingly complex instruments which take much, much more data at a time so that we use these billion-dollar facilities effectively. Turns out that one of the ways to use these telescopes very effectively is to do large surveys with smaller telescopes, which basically pinpoint the interesting things in the sky to study. So if you know what is interesting to look at, you don't have to waste any time with the big telescopes. And if you have the better list, you're more likely to be able to use that telescope effectively than other things. So these big surveys are extremely important for the future, and I'll talk a bit more about them. And finally, these big telescopes, because the data is so precious, we want to be able to reuse the data to undertake multiple projects. Don't let every photon you want to make count as many times as you can. So let's look at some of the ideas behind what I've just said. So you have the idea of surveys. This is a relatively modest telescope called the Sloan telescope. It was a 2.6 meter telescope. And the reason this telescope ended up being so spectacularly successful is because it was instrumented with what I would describe as an avant-garde, huge digital camera, which took vast quantities of data compared to what any facility had ever taken before. And that instrument collected data of the entire northern sky, or almost the entire northern sky. So this is just a projection of the northern sky, and if you zoom in from a very small region here, you can zoom in here to a nearby galaxy, the Triangulum Spiral for the amateurs, and if you zoom in more to the galaxy and then to the galaxy itself, you can see that the vast amount of data that was collected by this survey, it was literally, more billions upon billions upon billions of pixels. Now this created really a revolution in astronomy. It's the most productive facility in terms of impact in astronomy ever. The huge impact was not because of pre-planning. It was very successful when it set out to do, but the reason it was the most successful program of all times is because it enabled a whole raft of new science that was not expected at the time of the telescope being built. And it ushered in a new era of these huge data sets which people across the community could use to do their work. It ushered in the era of databases in astronomy. They had been used a little bit, but really not well known. Almost everyone now knows SQL in astronomy because of this. And this was a pet project of Jim Gray from Microsoft, who really went through and I think helped foster this along. So I'm always interested in doing, following on, and so I decided, well, Sloan has done the northern sky. I'm going to use a telescope in Australia to do the southern sky. And then I had a problem. My telescope was destroyed in 2003 with a bushfire that ran through my observatory. So like anything, you recover, and after 8 years, I am a proud owner of a new telescope called SkyMapper, which is a purpose-built facility to effectively do a survey in the southern sky similar to what the Sloan Digital Sky Survey did in the north. The difference is we're doing the entire southern sky, we're doing the sky 6 times, and in 6 different colors, where the Sloan Digital Sky Survey only used 5 colors and only observed it once. And so this provides an opportunity for us to do some new things, but also get that very important map of the southern sky to allow us to use those big telescopes effectively. So an image from this telescope, this has a 268 million pixel camera, and here's all 268 million pixels for you, showing the Lagoon Nebula for those who know about it, and the Trifid Nebula. And we would take, with this camera, 268 million pixels every 20 seconds to 2 minutes, so we can have a peak data rate of about 1 terabyte per night. The good news is, and then that turns out to be about 1 petabyte over the 5-year life of the program. Our databases are still, I would call, relatively modest, 10 to the 9 rows, about 20 terabytes in total. Now that turns out, thanks to Moore's Law in the 8 years that we have taken to get this facility up and running, is almost doable by normal people now using off-the-shelf technology. You can't just go into it blindly. We have access to a supercomputing facility called the NCI facility in Australia, and so they help us deal with this rate of data. And it's something we can do, I would not say comfortably, but we can do it without having to write hundreds of million-dollar proposal. Now, one of the things I want to feature, tell you is that it's great to have all this data, but the data you really need quality data in addition to just having data. Data is most useful if you're able to homogenize it. It's not well understood and calibrated. And so it's not a matter of just throwing data around. It's a matter of being useful, and science, therefore, needs to inform how this data is used in the future. In the future, SkyMapper is really just the beginnings of something much bigger. So there is a program in the US called LSST. It's, instead of being my telescope, it's a 1.3 meter telescope. This is an 8 meter telescope. And this telescope, purpose-built to do a massive survey, has a huge digital camera on it. size of a person with 3.2 billion pixels, so another factor of 10 larger than the one that we have just built. And the data rate of this telescope is astonishing. It will take approximately an image every 15 seconds, so that's 1.5 terabytes per year, 1.5 terabytes an hour, 5 petabytes a year roughly. The database, maybe not the way they eventually do it, could potentially have 3 times 10 to the 14 rows, so 40 petabyte database, and that's becoming an interesting thing to manage. You're not going to just have a group of astronomers who are ill-informed go out and do that. So optical astronomy, which I typically do, really pales into comparison to what work we're trying to do in radio astronomy. So in the Western Australian desert, Australia is in the process of building a new radio telescope called ASCAP. ASCAP takes data rates up to a new level. Radio telescopes are slightly different. They go through and they detect voltages from the sky, and then those voltages have to be compared with every other radio dish in the array. And so each one of these radio dishes in this telescope is grabbing roughly 2 terabits a second. Now, there's not a lot of information in those 2 terabits, so it's not like you're going to record it. You need to process it, get it through, and we typically use FPGAs, field programmable gate arrays, to deal with that in sort of a hardware solution. But eventually, you have to compare the information from the 36 dishes with each other. So that's 36 times 35 divided by 2 comparisons. And so with 36 dishes, it turns out, in this case, the computing that is done in the correlation, this is how you make images in a radio astronomy, is about 340 teraflops. And so that is a lot of compute power, which you cannot completely do only in hardware. It's quite a challenging process. So the ASCAP radio telescopes are being built now, but they are a prelude to something called the square kilometer array. The square kilometer array is to do the same idea of ASCAP, but on a much larger scale, with thousands of dishes looking simultaneously at the sky, spread out over the continent. Now, these things have to be able to communicate each other, so there's quite an interesting bandwidth issue of how much internet you need. And you need, of course, to have the computing power where instead of you're doing 36 times 35 over 2 comparisons, you might have 10,000 times 9,999 divided by 2 comparisons. So the computational power is remarkable when you go to these large scales. And so this is an extraordinarily ambitious project. Many would say maybe too ambitious for right now, but it is something that radio astronomy and Australia and South Africa, it turns out, are going to bidding right now to host this in the future that we have to look forward to. So to give you an idea of the amount of data that these telescopes are getting and how things are changing, 2008, one of the big 8-meter telescopes here in Europe was taking well less than a petabyte of data a year, more in the terabytes of data a year. LSST is taking quite large amounts of data, as in almost a gigabyte per second in the end when you add everything up. And the square kilometer array is getting up to a terabyte per second of data. And there are logistical problems which I'm hoping the people in this audience will help us solve. So one of the problems is just having enough compute power. If you go through and look at what ASCAP requires, it needs a serious supercomputer by modern standards, but at least it doesn't need the best one. But if you go through and want to make the square kilometer array work in all of its glory, you need to have a computer which is sort of #1 in the world, Moore's lawed out by another decade. And that means it is extraordinarily challenging. Now, astronomers and scientists are pretty good at taking shortcuts if we don't quite reach it. But the amount of compute power is going to be extreme no matter what we do. The other thing is it's not just compute power. So here's a diagram which shows 10 to the 10 to 10 to the 20 bytes, so memory, 10 to the 10 to 10 to the 20 bits per second, so internet connectivity, and 10 to the 10 to 10 to the 20 flops. And it sort of shows in this space where various things are. So we have here LSST, we have Google. So you can see that LSST and Google are about the same place. So in 5 years' time, I think we can assume, with a little bit of help from Google or Google-like organizations, we can probably achieve what we need to. The square kilometer array is very scary in this space because although the amount of sort of flops and bytes are not dissimilar to what we have, the connectivity is extreme, and so it really requires internet communications to advance a lot compared to what we're used to right now. The other thing we have to worry about is astronomers love spending money, but we don't normally spend our money on electricity. And the type of computer power that's required for these things, if you just scale it up right now, is on the order of 100 million euros per year just in the electricity to run the computer. So presumably we need better technology to make that a little cheaper. We also have other problems just reading the data. Astronomers like me need to read the data, and getting in these huge data cubes, for example, a 5 terabyte data cube, which is typically the basic unit of data from something like the square kilometer array, well, that's 500 seconds at 10 gigabytes a second. And so that's something, you know, that you're not going to achieve on a normal computer now. Hopefully in the future we can. But it means I can't just go through and do the normal type of analysis techniques that I'm used to. If you want to go through and load up the entire survey into the fastest computer, you're talking at 10 gigabytes a second of many, many days. And of course, the memory requirement's extreme. We don't have access to memory like that right now. So these are things, these are questions that are well beyond what we're able to do right now easily. So this is beyond the realm of normal astronomy, and so future astronomy projects really are going to have to worry about their processing storage facilities like we do not do now. And so these facilities are going to be special one-off facilities. We can't just expect every institution to be able to deal with the data on their own. And so because of the connectivity problem, I think the model that most people see is that you're going to have to work on things locally where the data resides and just move the information, so the value added between users in the facility so that the processing will stay local. So the way that we're trying to develop some of these tools is a toolbox known as the Virtual Observatory, which really empowers astronomers like me, hopefully in the data era, to get down and do our work. I want to do astronomy. You know, I do a lot of computer programming, it seems, but it's not really what I'm good at. And so the toolbox that's being worked on is the thing that hopefully will empower us in the future. The community has spent a lot of effort over the last decade developing tools to get our answers to scientific questions. Now, one of the things is just simply getting archives of data. So the Hubble Space Telescope was one of the first facilities to really go through and do an archive and do it well. And so although the archive is growing with more and more data, the interesting thing is that each one of, on average, the data is retrieved many, many more times than just once. So I might go out and have a program, but we're finding is that more and more papers from that are in astronomy that are useful are actually reusing someone else's data, and having an archive to do that is the first step. But as you get more and more archives, things get complicated. And so one of the things we have now are registries of archives where people can sort of publish what their archive looks like in a set of standards. And so here I've just gone through to one of the tools that's available on the web, and I can go through and say, for example, 47 Tucanae is a globular cluster down by in the southern sky. And you can ask the question, of the 9,503 available archives, what's got data? And I can even go through and specify I want optical data, I want radio data, whatever. So this is a way for people like me to navigate through the sea of data quickly to ask our scientific questions. So, for example, one of the things that we have are images from different surveys. So the tools enable us, for example, to quickly ask data from any of these VO compliant survey. You can do this by hand. You can use a set of programming libraries. Astronomers are particularly keen on Python right now. It's what I would typically use. And so, for example, here is Centaurus A, which I went through and just picked out an image from one of the surveys. And then I could ask the question, well, give me a radio image of this same galaxy. And that radio image looks like this. So this data sets, which had never talked to each other, I was immediately able to overlap. And this is a galaxy, what we call an elliptical galaxy, mainly old stars, that's eaten for lunch a little galaxy that happened to get a little close to it, and so it's ripped it apart. And inside this galaxy is a black hole. And that black hole is shooting jets out which appear in the radio. And so the black hole we think is in the middle, and these jets are being shot out at relativistic speeds from the center of this galaxy. And this is something that's been known for a lot, but it shows you how an astronomer would go about and try to look at data from different data sets. And of course, there are 9,502 other catalogs I could go through and search right now. And that's increasing because the publishing tools are sort of more or less automatic now. There are some quite big challenges in the future. So rather than look at images, it's much better to look at catalogs of data that people have already got and told you what the information is in the most accurate form that you can. So here, for example, is an image taken with the Hubble Space Telescope of 47 Tucanae, the globular cluster I referred to earlier. And how to match up objects is not obvious in all cases. So for example, if I take the photographic survey, that's what it looks like. And to have some sophisticated way of telling you which star is in common, not so easy. And so we need to have sophisticated tools of going through and making clever decisions about how to match things up and to put information together. And so that's an area I would say is still being developed and something that's going to be extremely important for people like me to use in the future. We also have other things, such as I like to study transient events. Different people around the world are going through and looking for these, and we want to share information. And so through something called VO Event, you can go through now and you can publish information on these events, and people like me can go through and subscribe or go through and query this information as it comes through and make intelligent decisions on my behalf and then add information to these events. So let's say that Tycho Brahe 2 discovers a supernova. He could publish it on this. I would have my telescope in Australia say, oh, there's a new supernova. I would observe it and say, it's a type 1a supernova, the ones I'm interested in. I could publish that on there, and everyone can follow what's going on. And there's a whole range of activities and information we can do. So these are the type of tools that people like me need to use. The data mining and data discovery is another area of active research. How do you use all this information to learn new things? And this is an area, I think, of active research. So Jim Gray's fourth paradigm, as he would call it, is you got observations, you have theory to understand. That's traditional physics. You have simulations, which is part of the theory. And then you have the whole idea of data mining and taking these vast collections of data and trying to make inferences from it in as systematic and useful way as possible. And as I said, this is an area that I think is still rapidly developing. The tools astronomers sort of play around with, but I think we're still getting used to them. Another interesting thing to do, which is sort of an interesting way of looking at data mining, is to do it by brute force, using the real neural networks around the world, citizens. So one of the more effective things that people have been able to do is go through, for example, and use people who are interested in discovering supernovae in your data or in my data. And you can go up and present them things, and they can say, yeah, that looks good. Because one of the problems we have is we have defects in our data, and sometimes our programs get fooled. And you can't just say, oh, I'm sure without looking at the data, I'm going to send the Hubble Space Telescope to go look at this supernova. You really have confirmation. But the citizen scientists are actually good enough. Their programs, if you have enough of them, tend to be controllable, where you can go through and actually make honest-to-God decisions, probably not life or death decisions, but pointing a telescope decisions based on that. And it's a great way to do outreach as well. And so this is one of the interesting new things that is going. I think you have a responsibility of doing interesting work that's hard to do otherwise with this, but it does seem to be something that resonates with the community. And you have the advantage that sometimes you find things that you don't expect. And so in the case not looking for supernovae, but looking at galaxies, this object, which we don't still really understand what it is, was detected. And so giving pause for people to go out and try to learn what's going on, because that object in many of our algorithms we would have just thrown away as probably an image blemish because it doesn't look like what we normally are trying to study. And so you can find the unknown this way. And finally, we have new age media. So for example, you can do things like Twitter. Here's an example of a supernova in the Whirlpool galaxy, M51, where someone put it onto Twitter and said, immediately after discovering, and that allowed amateurs to go out and get their telescope and look and confirm the observations essentially in real time. Amateurs with their new telescopes sometimes can do things, mainly because there's so many of them so quickly, that are really useful for doing the science that we're doing. So where are we going in the future? Well, astronomy is going to be relying on using information and technology to continue to rapidly advance over the coming decades. That is just the basis of our science. Handling our data sets, largely done by computer literate astronomers, will need to become professionalized. That is, people like me just are not equipped anymore to deal with the amount of data we're going to have. I'm going to be a user rather than someone trying to make things work myself. Future telescopes, I think, are going to have IT specialists at the core of the building team. They're going to be integrated into our programs from the very beginning, because that is such an important part of the future instrumentations. And the scientists still need to provide, I guess, input into the specific types of information we want out of the facility, but people in this room are going to be there to actually make sure that it can happen from a technical point of view as well, and inventing new ways to sift through the data. I think will be quite synergistic in the future. Astronomy itself, I think, remains interesting because it's a place to innovate. Our data sets are large, they're big, and they're not, classified material. They're actually interesting sized. You have at your disposal 5,000 to 10,000 quite computationally literate users who can go through, and you don't have to worry so much about the GUI, is just getting the thing to basically work. We'll go through and give feedback. And I think we also still have big, interesting questions which can help captivate the public in the work that's being done. And I'll stop there.
Thank you very much, Brian, for this interesting and enlightening talk. I'm sure there are a couple of questions that people want to ask.
I've stunned them into silence.
Yes.
I really have stunned them into silence.
There we go. In the back.
So the LOFAR activities are starting up in Europe. So could you compare the data rates you have in that, if you know, towards the SCAR rays and the ASCAR?
So LOFAR, like ASCAP, is a sort of, it's something that is coming in advance of the square kilometer array. Now LOFAR has a couple advantages that makes the problem a little more tractable. First of all, it's not in the Western Australian desert, so that means your internet connectivity is pretty good already. It also works at lower frequency, and that turns out means you don't have to do as much computation, but it has more antennas. And so together, LOFAR is a very interesting problem. It essentially is like ASCAP to, within a factor of 5 or 10 in terms of computational demands. And so it is preparing for the next generation of telescope in the same way that ASCAP is. And so from my perspective, it's, as a scientist, it's a great experiment, and we are doing a similar experiment in Australia as well, where we think our slightly less or more radio quiet skies, there's 160 people within 200 kilometers of the radio telescope. And so there's some really fundamental questions that we can answer with it. But I would say in terms of scale, it's similar, and we're actually using a similar approach to solve the problem between the two facilities.
In comparing different wavelengths, I mean, is there now I gather it's difficult to actually correlate objects necessarily. So are people using machine learning technologies to actually go and identify common objects in different wavelengths?
I think we're trying to. It's not clear to me that those have been developed. So the problem was, so I showed you an example where you have very different looking images and you have to figure them out. If I were to show you an image in the gamma rays and show you one in the optical, that you really need to be smart about. And so the problem we have is if you're going to use a machine technique, you need to have enough samples to train up your objects so you can just do it. Often we don't. And so then you need to use your physical intuition or your physics to match them. And so it's a place where if you have lots of objects, you can use some of these techniques. I would still say that that's a work in progress, but we're always going to need to use physics. Or I say in many, many situations, we're going to have to use the physics to inform the comparison as well. So I would say George Dragowski here in the front has worked more on the actual machine learning stuff than I have.
You talked about the need to have IT specialists in the building teams of these large instruments. Do you believe that data management technology exists and can solve all your problems? You just need to have the right expertise for it? Or do you think that even research in that area needs to be done to answer more complicated questions or structure your data differently or whatever else?
So being clever, which is the way to deal with the data management, is going to be imperative. I've shown you the amount of data we have, and if it's taking 5 days to read it once into memory, being clever is really important. And so I think coming up with better and innovative ways to solve the problems will be paramount for us to move forward. And so we've had various things of hierarchical data storage come out, which are, 15 years ago I'd never heard of, and I'm like, oh, that's a clever idea. And that's the type of stuff that can come out from there. And so I do think that will be a key. We don't want to just brute force this. We really want to be clever. And so that's where I think everyone here will come into the foray.
I'm very sorry for asking a different type of question. On one of your slides was that everything will be driven by scientific problems. So I will ask a simple question. Which are scientific problems in astronomy now?
So what are the big questions in astronomy? So there's a whole range. I think one of the most interesting ones for me, in addition to when I discovered the accelerating universe, that indicates that 73% of the universe is something we call dark energy, which is potentially energy tied to space itself. We don't really know, we don't understand. So that's a big question. What is this stuff that we have discovered that causes the universe to expand at an ever-increasing rate? But I think another question that's coming in, which will be the question of this decade, is technology is allowing us to look back to about 200 million years after the Big Bang, when the stars and galaxies, which we see everywhere in the universe today, were formed for the first time out of the sea of hydrogen and helium that was synthesized in the Big Bang. And so that technology to look back to that time and actually see the universe being born is something we will have over the next decade. And it's my hope that that's one of the great things that, for example, the square kilometer array can go back and see the gas itself. It's sensitive to gas. We're able to see that gas sort of be transformed into stars and understand how the universe was born. So to me, that is the fundamental question, along with, is there life on other planets? And that's another one that's quite different, not so much cosmology, and that's something I think that can probably be done in the next 30 or 40 years, probably with the technology. We'll be able to see the signatures of life in distant planets.
You talk about data quality and defects in images. What is the best time point to detect those defects in the image? At one time, when you shoot those images, or when you store it in a database?
So we use a whole range of techniques. I mean, we often know there are some problems, but so we have a catalog of defects we keep track of, so we get rid of those. Then you have the things that you just can't predict. A satellite, which you didn't know, or a meteorite goes across. And so you have to have algorithms. But inevitably, as you have more and more data, you have different types of algorithms to identify the defects, but you get fooled sometimes. And so inevitably your database gets polluted with some fraction of things that you just don't want to be there. There's no way around it. It's just fewer and fewer as you get along. The difficulty is for people like me who are looking for the really odd event. So I go through and sift through a petabyte of data, and I got a million things out of that petabyte of data that are interesting, and then I got to deal with a million things. And so that's where things like machine learning and things can come out and say, well, actually, I'm just going to dump those things into this program, and it's going to go through and say, well, 85% of them look like this class of object, 5% look like this, and then there's about 7 or 8 things which we just don't understand, and I can go through and look at those different groupings. And so I think that's sort of the way we deal with things at this point. You really want to clean things up as best you can, and it's a matter of just getting the bad stuff to be as small a part of it as you can.
My colleague is evaluating the physical fundamental constant.
Yes.
And we deal with velocity of light as exact constant.
Yep.
Such a happy day will continue for a while, or do we need to change the velocity of light?
So, I'm a belief, there's nothing absolute. You always want to test everything. And so we have seen recently potential evidence that possibly neutrinos are going faster than the speed of light. So that's a very interesting thing we need to examine. I would love for that to be true, but we need to literally do more and more science to test it out. And we'll know within a year whether or not I think that experiment is right. At least that would be my hope. In terms of the speed of light, again, we can test it. And one of the things that some of my colleagues have done is to infer not so much the speed of light has changed, perhaps the fine structure constant. So a fundamental thing that tells you how atoms are put together is changing back in time. An interesting experiment, again, better, more data, better data, asked to go in and probe that thing. You need to convince your colleagues. We're a very skeptical lot in science. And so really you get to things not by saying, no, I refuse to do anything, question the speed of light. You go out and you test it. And you test it better and better and better, and that's how we learn, is by finding mistakes in what we already know.
Hi. Is there any correlation in between what you are discovering looking up there and what is being measured at CERN, since you both talks about Big Bang, universe, etc., etc.?
So 25 years ago, very little was overlapping, and now more and more. So the dark energy that the accelerating universe we think leads to this idea of dark energy. And one of the ideas that what makes dark energy is how quantum mechanics works, and possibly how quantum mechanics works with gravity. Now CERN is probing particle physics, trying to learn how most of the forces of nature other than gravity work. So our cosmology gives us a way to connect in, potentially, into the work at CERN. But we don't quite get it all. We don't have a solution. We're really looking for an inspired person, a new Einstein, to try to piece it together. The idea that CERN has done, again, with these faster-than-light neutrinos, well, that feeds in directly to astronomy as we do. We had a supernova in 1987 whose neutrinos and light got to the Earth at essentially the same time. And so if that experiment at CERN is correct, reconciling it with those astronomical observations will be an important insight to the nature of what would be causing this. And so we can work, I think, more and more together as the science progresses. So we don't have any answers yet, but yes, I go to a lot of conferences now on particle physics that I never dreamed I would have done when I started my PhD.
Okay, so then let's thank Brian again. Brian, thank you very much for coming here.
Oh, my pleasure.
I have a little present for you,
Okay.
which is a Lana horse.
Yes.
A typical Swedish souvenir. I hope
Okay.
you have some use of that. Thank you very much
Thank you
for
so
your
much.
time spent with us.